Hello, I'm Rich Eisenberg, Editor-in-Chief of Inorganic Chemistry. As part of our 50th anniversary year, we are having interviews with leaders of the field. Today, we're doing an inorganic chemistry first. We're interviewing a couple, not just one, but two preeminent inorganic chemists. Our interviewees today are Professors Don and Marcetta Darensbourg, both distinguished professors from Texas A&M University. Both Don and Marcetta have won ACS awards in inorganic chemistry and have been active in the Division of Inorganic Chemistry, have been leaders for a number of years, and for full disclosure, have been good friends of mine as well. Welcome, Marcetta. Welcome, Don. It's a pleasure to have you here today.
Thank you, Rich.
It's good to be here. Thanks.
Let's start with your early years, and how did your interest in science develop? Separately, let me start with Marcetta, and then we'll go to Don.
Well, my parents, of course, were the biggest influence on me, and they were school teachers, and I'm from the hills of Kentucky. They were fairly well educated for the hills of Kentucky, and they encouraged me in everything that I've done. My dad was sort of a gee whiz scientist. He was always looking for special things. But I'm sure had he been trained, he would have been a good scientist. I became a chemist because of my high school chemistry teacher, Mrs. Bolton, who I really admired and wanted to be just like her. So then I went to Union College in Barbourville, Kentucky, and on to the University of Illinois for my PhD.
Okay, we'll get to Illinois in a second. Don, how about you?
Well, I grew up in Baton Rouge, Louisiana, and science wasn't a big part of my background. I went to private school, which really had a very weak science curriculum. And my father was a builder, though, and so I was always encouraged. He was good at math. My sister actually majored in math in college, so we were good at math, but science I had very little of. So what I decided to do was to go on to college and be an architect or mechanical engineer, because that's what I was familiar with. And after arriving in Los Angeles for undergraduate school, I really didn't like the mechanical engineering curriculum, and we were required to take freshman chemistry. And I really fell in love with chemistry then, and eventually went on to do undergraduate research with Harold Goldwhite at Cal State LA. And from there, it's sort of history.
Do you think some of the architectural elements that are in chemistry are what really attracted you?
I think building molecules is very much akin to building buildings.
Okay.
It's that same idea, and the same satisfaction one gets from making a molecule, determining its structure, et cetera.
Tell our viewers where you went to graduate school, with whom you worked, and what you were doing in graduate school. I think you met in graduate school as well.
Yeah, of course. So I went to Illinois, University of Illinois, Champaign-Urbana, and decided to focus on inorganic chemistry, since that's what I had focused on as an undergraduate. Worked in the area of infrared spectroscopy with Ted Brown. I started actually with Stan Piper, and he passed away during my first year. So I switched to Ted Brown, and was the first member of his group to really get involved in metal carbonyl chemistry. We did infrared intensities, which was a rather odd thing to be doing as an inorganic chemist, but you had to synthesize organometallic compounds. So that was the early stages of organometallic chemistry. I actually never had a course in organometallic chemistry because one wasn't offered.
Marcetta?
Well, also at the University of Illinois, and I actually had a bit of a hard time finding a group because some professors didn't want women in their group at the time. But that was the most fortunate thing for me. I ended up with Ted Brown. And he was a wonderful mentor and a very cautious, careful scientist. I probably was the last student to work on his organolithium projects, and he was working on catalysis using anionic polymerization catalysts for olefin polymerizations. I really enjoyed those years. I thought everything that was going on in inorganic chemistry was there at the University of Illinois. And I think I was right for all the physical methods that Russ Drago was developing, the start of materials chemistry that Galen Stuckey was developing, and so much more that I could talk about from those days.
Now, this was sometime in the early, mid-1960s?
I graduated in '67.
Okay.
68.
Yeah. Now, did either of you do postdoctoral work?
Actually, not. My first job after graduate school, after 4 years of graduate school, was at Texaco Research Center in Beacon, New York, which is upriver from the city. And of course, I went there for a reason, and Marcetta can explain that. But I worked with a guy who was very well known for doing adsorbed small molecules on supported catalytic surfaces, a guy named Bob Eischen. So it was sort of a postdoc, but I was paid better than a postdoc. And I had lots of time because of the way industry operated at the time. I had full-time technicians and really wasn't allowed to do much work in the lab myself. So I had lots of time to think about proposal writing, et cetera, and almost immediately decided I wanted an academic job. And Texaco was very nice to me. They allowed me to work for 8 months after I had obtained an academic job.
Very good. Marcetta?
And I also did not have a postdoc immediately after graduate school. I took a position at Vassar College, which is a wonderful undergraduate institution, the best students, and had a research lab, which Don frequented as soon as we were married and together for a couple of years at Vassar. We did some experiments together and published work from that time. I did have my version of a postdoc came with my first sabbatical, and that was with Earl Mutertes when he was still at Cornell. And in a lot of ways, that really gave a huge boost to my career, and he advised me to go study hydrides, Marcetta. And it was sort of like plastics, if you know what I mean.
Yes, I do. I do. Actually, I should point out for our viewers that in the mid-'60s, postdocs were not necessarily as required as they are today in terms of getting faculty positions. Now, let me turn back to this idea of from these early studies, what kinds of threads or themes ran through your research from then until today?
Well, I was interested in charge distribution in molecules and how you might probe that in some way with reactivity. We worked together on this because Don was the infrared spectroscopist who understood force constants in metal carbonyls. So we could map this nucleophilic attack on metal carbonyls, in the production of acyl from neutral metal carbonyls and carbanions. So that charge distribution idea carried on for me in my first work with site-specific ion pairing, and then from there on into hydrides.
Yeah, and then you continued into bio-inorganic chemistry today with iron hydrogenase models, and there is a link.
Oh yes, oh yes. I think those fundamental studies that we did with metal carbonyl hydrides and just metal carbonyl anions led to my seeing or my interest in finding some hydrides in biology. And I thought that the best place to look for those would be in the hydrogenases. And I started thinking about that before the structures of the active sites of the hydrogenases had been established. So I first got into coordination chemistry using nickel into S2 compounds. And all I am today, I owe to two molecules, actually. A molecule that was synthesized by Dan Mills in my research group, which has a square planar nickel and into S2 coordination. And I was we were very fortunate in seeing a lot of reactivity at the sulfurs of those. Then from that, I went into the diiron hydrogenases. But we can talk more about that.
We'll get there, but let's give Don a chance to catch up. And yeah, so in terms of the threads and themes as they were established early and how they evolved to today.
Yeah, well, from the very start, I was interested in mechanistic, inorganic, organometallic chemistry. And I had this specialty in infrared spectroscopy background that was very useful at the time. And in the early 70s, because of the fuel crisis, inorganic chemists or organometallic chemists were very involved in Fischer-Tropsch type chemistry. And so the reaction I elected to investigate was a water gas shift reaction, which converts some of the CO to hydrogen. And during that process, CO2 is a product of that reaction. And so for many years, we went through studying the mechanism of CO2 reactions into metal hydrides, some of which Marcetta had synthesized and were well characterized. And that evolved to looking at CO2 insertion into metal carbon bonds, metal oxygen bonds, and at the same time employing in situ infrared techniques to monitor reactions at whatever conditions, high pressures, low temperatures, etc. And from there, looking at making small molecules with CO2, and eventually progressing to making polymers, which is the emphasis of our work today.
Now, this interview is unique in the sense that I have the two of you here, and while it's still not common, it's certainly more frequently encountered that scientists become life partners as well. And I think that a lot of people would be interested in how you handle that transition, how you handled moving from being a couple and locating yourself in a single position or a single place and handling all of life's other challenges at the same time that you're being professional colleagues. So let's talk about how that started, because you took a long path to get to A&M, I think.
Yeah, and certainly in those days it was not as easy as it is today. I think universities understand today that a couple is a lot more stable than a single in terms of relocating. So there's a significant amount of stability in two. But initially we traveled a pretty bumpy road. As we said, I was at Texaco, which was down the river from Vassar. I wanted academics. The place where I got a job was the State University of New York at Buffalo, which was a nice place. There were issues with the weather. Marcetta was, of course, not so eager to give up her Vassar position to move to Buffalo, where she didn't have a permanent position. She had a rotating kind of position. And so it just made it difficult. But eventually, things worked out. So I think there's a lot of compromising that goes on. There's a lot of times when you're going to be separated. So it's just a question of how serious you are about making this work. I think today it's a lot easier. Universities understand it and make a real effort to accommodate couples.
Now, Marcetta, you didn't have that faculty position in Buffalo, and I know about the weather in Western New York. So what happened next?
Well, there was a point when I think it got very rocky with the marriage, and I did feel that I wasn't getting a rewarding position. So I started looking for a position of my own, and Tulane came through for me. And it wasn't so terrible because Don's parents were just up the river. So I could see them on weekends, so the connection was very strong to the Darensbourgs. And within 2 years, Tulane hired Don. So we spent our coming through the ranks years at Tulane, and I'm very grateful to them for taking the two of us. Tulane's always had a strong inorganic division and history, and we were a part of that for that time. And then Don had a sabbatical with Al Cotton, and Al decided, I think, that this would be a good hire for Texas A&M, and the two of us. And we moved together to Texas A&M.
How many years were you at Tulane, and then?
I was at Tulane for 12 years, and Don was 10.
10.
Mm-hmm. Okay.
But I think once a university like Tulane is willing to take a chance and you get tenure, then all kinds of opportunities open up because they have taken the chance to show that it works. Mm-hmm. After that, it's easy. It's an easy decision. So we were lucky.
Good. One simple question. What advice would you have? It's a simple question to ask, the answer may be long. What advice would you have for couples today starting out?
Well, somebody is going to probably have to compromise at the beginning. And that compromise may be shared. It's your turn now, it's my turn later. And we've seen that with some of our friends who are academicians. And of course, everything is different when there's children. Don and I didn't have children. We have horses and other family, but we don't have children. So but we see more and more that the stay-at-home dad or many of my students, my women students who have ambitions to be professors or high-level positions in industry, have seemingly to me chosen a partner who will be very supportive and will have a flexible job so that they may be teachers, they may be in medicine, so they can move around. So I think if you just look ahead at what the problems might be and think about it a little bit in advance, try to make the plans, but if the plans don't work and you have to take a different course, don't look back.
Good advice.
Yeah, it's not easy. But I think, as Marcetta said, there is some compromising that has to be done. But what one wants to do is be realistic about the situation. Try to find places that you will both have a successful and a happy life together and a successful career. And I think I'm always reminded of what my mother told me about marriage. And that was that marriage was just a lot of compromising, and that both parties would feel they were making all the compromise. They were doing all the compromising. And of course, that's going to always be the case. But I think one advice I can give to young couples is that when they do elect to look at jobs, they should be very straightforward with their employer. I think they should let their potential employer know that there's an issue, because they typically will be interviewed one at a time. And being upfront is a lot easier for everyone than after the fact.
Let me turn to back to the science and ask you what your proudest or most important, they're not necessarily the same, proudest and most important research accomplishments. What would you identify there?
Yeah, that's a bit of a tough one, but you know, I've always sort of demonstrated the use of infrared in doing reaction mechanisms, et cetera. So I sort of developed a little bit of a reputation with using specialized equipment, et cetera, and that was always pleasing to me. But I think where I'm most pleased is when we started doing these CO2 polymerization reactions, which we took up work that was done in the early or late 60s, early 70s by Inoue in Japan. It had sort of gone along with a lot of heterogeneous catalysts that were very ineffective, and we all sort of beat our heads against the wall trying to figure out how these worked. And I got this student from Mississippi, Matt Holtkamp, who had the bright idea that why are we doing this? You know, why don't we find something new? And he came up with these very sterically bulky zinc complexes, which were homogeneous catalysts, and that really broke the field open. We published that paper in '95, and from that day on, hundreds of papers have come out in the area. So that was a very pleasing and exciting result for us.
Marcetta.
Well, when I switched from fundamental organometallic chemistry and stuck my toe in the waters of bioinorganic, this was just at the beginning of the opening of the field of hydrogenases, and a field that is very broad and has all sorts of scientists involved in it, because these hydrogenases do hydrogen chemistry just as platinum does hydrogen chemistry in fuel cells. So it would be wonderful to understand these active sites that are comprised of iron and sulfur and sometimes nickel in an elaborate molecular configuration. And we inorganic chemists, organometallic chemists, might be able to understand some of that. And then it was discovered that there was carbon monoxide and cyanide in these active sites. And so the first molecule that was so important to me, Don helped me find actually, is just the piano stool CP iron carbonyl dicyanide. And we showed that that was a direct mimic of or gave a direct mimic of the infrared spectrum of the active site of nickel iron hydrogenase. And from that, I mean, that was very exciting when we saw that spectrum. It just overlapped completely with the enzyme. And, you know, I figured out chemistry is chemistry. It doesn't matter if it's in the middle of an enzyme or in an infrared cell of a compound that we've made. Then my nickel into S2 chemistry came together with iron chemistry. I used metallo ligands, the nickel into S2 as a metalloligand to bind to iron tetracarbonyl. And all of a sudden, the hydrogenase spectroscopists were calling me and inviting me to meetings and inviting me to give lectures on these organometallics. And I have to say that that community was very welcoming to me. And all this time was so exciting because it was totally new. And I was so happy to be able to contribute my knowledge to that. So then in the final molecule that is so important to me came from the diiron hexacarbonyl precursor to the iron active site in diiron hydrogenases. By that time, my able competitor, Tom Rauchfuss, was in the game. And when I saw that structure come out from the protein crystallographers of the diiron hydrogenase active site, I said, oh, we all know what that compound is. Let's go in the lab and make it really fast because Tom's going to be there soon. And it was, boy, was I right on that. So Tom Rauchfuss, Chris Pickett, and myself all published the first models of that system simultaneously within the same year. That opened sort of a floodgate of models for the diiron hydrogenase active site, the hydrogen producers. And then I wanted to look more deeply at what the enzyme active site was. And what nature has done is, and has always done with these metalloenzyme active sites, is to use the protein superstructure to change our ground state structures that we can make in the laboratory. But all of the protein superstructure can twist and distort coordination sites to make the redox potentials and make the reactivity just slightly different, just different enough so that they can do reversible catalysis, as is prominent in enzymes. So we wanted to go from this butterfly shape to an inverted butterfly shape in the diiron dithiolate. And how to do that? Well, I had two wonderful students who were actually competing with each other at the time. And Tianbiao Liu was the first one to put together the abiological ligands to enforce this structure. And Mike Singleton later did this. And I should mention these students are, of course, our greatest accomplishments.
That's right. That's right. I was going to ask about something a little different, rather most important or proudest, which is the sort of, quote, eureka moment, when something is wow. I mean, for me, it was as simple as finding out that a phenyl ring really does have 6 carbons and it's flat, and that came out of a crystal structure. But you had mentioned the infrared spectrum and the matching of that. How about you, Don, in terms of special moments?
The earliest one was this correlation between CO force constants and charge on carbon and nucleophilic activity. I think that happened very soon. And in fact, we published a major paper in Inorganic Chemistry in the very early 70s on that issue. So that was one of the first things. In terms of other moments, I guess, I'm now sort of work in the polymer community, and I was totally unaware of synthesizing polymers, et cetera. And I think learning about stereochemistry, tacticity, et cetera, that was when things really lit up, because I'd always heard lectures, et cetera, but sort of never really got into it very deeply. And until one gets into asymmetry and asymmetric catalysis, et cetera.
Do I remember right that in the early years of your research, you had somehow a big supply of C13 labeled CO that you were using for all kinds of exchange reactions that other people were not doing?
Yeah, we learned to make regioselective metal carbonyls labeled in carbon-13 CO. And in fact, I wanted to mention a paper, my inorganic publication that has the most hits is a little note that I published with a second-year undergraduate at Tulane. and that was making metal dye-substituted metal carbonyls with amines that were fairly labile so that you could make, and they started out in the cis configuration, but you could make mixed phosphine amines that were cis or trans, and then you could dissociate that second one and replace it with a carbon-13 CO stereoselectively or regioselectively. And that paper has got nearly 300 hits over the years. But it was a simple idea. But in any case, then being able to make stereoselective metal carbonyls, we could do substitution reactions. We had infrared spectrometers. Later, carbon-13 NMRs were readily available. So we were well established. We were poised because we could make the materials and had an interest in mechanisms so that we could actually study their reactivities and look at rearrangements, et cetera.
It's great that you did that also with an undergrad initially.
Yeah. Well, at Tulane,
Tulane,
we had very few graduate students. I think over the 10 years I was there, I produced 3 PhDs, and one of those 3 finished up at A&M. So there were mostly undergraduates, but they were super students.
Well, there's a good message too for people who are interested in research and in teaching, that you can do a lot.
You can do a heck of a lot.
Yes.
If you're involved. The students are very enthusiastic, they're bright, they know no limits. They're not inhibited like we are. So it's a super opportunity.
Yeah. And you mentioned advice to couples, but maybe this has to do with advice to research groups, and that is marshal your forces. You know, you can use undergraduates, the undergraduate synthesis lab. There's all kinds of work that you can get done with your students by sort of directing them in ways to do reviews of the literature, as well as to make starting materials in the laboratory. That's easy.
Now you've once you got to A&M, you both have substantial groups, and that's continued on over the years. What advice would you have for young scientists today in terms of how to think about running a research group and you know, getting started in that manner, besides marshaling your forces, or in addition to?
I think probably one of the biggest advice, and things are so different than when we started. You know, one goes into a position now with a lot of startup money, and so the opportunities are somewhat different. But in any case, I think the biggest mistake a junior person can make at most institutions is to assume that if you just send the graduate students in the lab, something's going to happen. I think in the early days, you have to be very involved with the lab setup, with helping students, with being a good model for them in hard work, passion for the research, treating it so that they take on the pride and make the work part of their efforts. Ownership. Also, they should start thinking then in terms of careers as opposed to jobs. I think students sometimes think of chemistry as a job, and I think a real chemist think of it as a career. So so there's a lot you can do to encourage students to be passionate and to work hard, et cetera. And also, I think it's good to think of them as colleagues more than workers, because that really establishes them then as scientists themselves, and treat them with a great deal of respect. Expect a lot of them, but treat them with a great deal of respect as well.
Yeah, it's a real challenge and talent to be able to stimulate the word that you used, Marcetta, was ownership, student ownership of research project and how they become colleagues rather than just students. And this is very important.
You know, sometimes we say we aren't trained to manage a group. We aren't trained to be managers. We're trained to be scientists. But I think being trained as scientists is the best way, because each of those students are different, and or postdoctorals or whoever we're working with. And so we do have to look at the project, look at our overall goal, and make sure the student understands what their part is in achieving this. Of course, we're always working in this, you scratch my back, I'll scratch yours. They work hard for us. They help us with our passions, our dreams, our ideas, getting our next grant, and we help them at the base of their career. Of course, we help them later on too, because we're always in contact with the students.
What would you advise students today with regard to how they communicate their research? I assume you have your students doing writing of papers, drafts, and what have you. But as to new faculty members today, how should you communicate, or what advice would you have for communicating your science?
Well, first of all, they should be going to meetings, and some of those meetings they should be there to learn, and perhaps not necessarily talking right away, presenting right away, but definitely in their overall picture, their big goal should have various vignettes that they can finish in a reasonable time. Remember, when tenure comes, there has to be papers out there that have been reviewed. So in putting together their research projects, their research goals, it should be something important, something significant, but within that, select out the small parts that can be finished, always completely, as complete as can be at this moment in time, but don't feel that you have to write 20-page papers. Get something finished.
Do you think that there's too much of a driver today with regard to application rather than fundamental science in the work of people, or how they're framing what they're doing?
Yeah, for me, it's never been an issue. I've always not had a conflict between doing fundamental science and seeing an application. But I think, yes, one should be careful then to choose an application for which they're not capable of making very fundamental contributions. You know, as things go in and out of fad, one has to be very careful that they have the expertise and the ability to make serious contributions to those areas prior to worrying about the application. Being always involved with catalysis, et cetera, there's always been a direct link to some application. And that's become more prevalent in my research now with green, sustainable type chemistry that we're doing. But I think there needn't be a real conflict.
I think that's an important point that you just raised in terms of choosing an area or choosing a problem for which you can do both fundamental science and have the potential application, and that the two can feed off of each other well. How about funding today? Because in fact, funding is a question we all face, both in terms of acquiring it, its availability, and also the drive for what is it going to do for our economy, for example. So what advice would you have for young researchers today about how they acquire funding and how they move forward in terms of their research?
Well, you know, the traditional way is to have the good ideas and to write the good proposals to the 3 or 4 major funding agencies. I think connected to this is the network that the young person might be developing as they choose projects within a community of scientists. Again, not repeating everything that's in that community, but finding their niche and getting to know people, developing colleagues, developing collaborations perhaps, but certainly developing a network of people that you can talk to. And this will help in the maturation of their ideas. And serious collaborations can be greatly helpful. I have a serious collaboration with my call in my department, and that is very good for both of us, I think. In my early days, I had Jack Halpern sit down with me, and I went over my ideas, and he encouraged me. And that was a mentor type thing that gave me confidence in writing proposals. I think the elegant experiments will always be honored with dollars. So whether it's, you know, strictly applied or not, if there is a need for something to be done that will make science progress, that will be honored, rewarded.
Hope it's true for the elegant ideas.
Yeah.
Before the
Yeah,
elegant results. Yeah. Don,
Yeah.
your thoughts?
Well, I think, you know, certainly I've seen what a community can do for you, because it was very late in my career that I got involved with the polymer community. And it takes a little while to get accepted. I mean, when I submitted my first paper to macromolecules, it did get accepted, but it was a little bit rockier than normal because I was sort of entering a new area. But the community has been very welcoming and have taught me a lot. At the same time, I think, and this might be an issue with young faculty, often they're a little bit inhibited about taking a lot of mentoring from their colleagues because they're worried too much about their colleagues being judgmental. So they often are not as interactive with their senior people as they probably should be. I think we can give good advice. But I think what Marcetta said about the community is extremely important. I have a very supportive community in this polymerization community. Chisholm, Coates, Nosaki, Lou, all over the world we interact. And I think it makes it fun because we're competitors, but at the same time, we're friends and we're scientists with some sort of a common goal to solve major problems. And that I find to be extremely rewarding, and that's happened later in my career than in the beginning of it.
How do you think chemical research will change in the future, especially from what it was when we started?
Yeah.
But projecting ahead, how do you think chemical research will change? And I think, Marcetta, you hit on what some of the enduring qualities have to be. So let me ask you that. How will it change?
Well, one thing that worries me a little bit is that we become too organized into large groups that are somehow interacting via internet or what have you in a very formal way. I think good research is always going to be done by individuals. They should obviously be interacting, and I think interactions for me have always been natural. If I need to know something from someone, I send them an email or I call them. And I don't have a formal relationship with them to interact. So I worry a little bit if science becomes too much as a group interaction, that it will somehow inhibit these individuals from, going in various directions, which often are very, very fruitful directions. But I suspect it will change because it's just a lot more interdisciplinary. We're working on bigger problems and problems that one person can't possibly address alone. So I think that's where the bigger changes are going to come in how we handle that to still keep PIs, principal investigators, funded so that they can develop to be really strong contributors to any group interaction. That's going to be critical, how we solve that issue, because the funding level is going to, those two areas are going to be in conflict for the same funds.
I take your question a little bit differently in terms of the type of chemistry that we're doing. If I look through my career, I saw at first physical methods were coming in, and X-ray crystallography was really difficult. I had to bribe Jerry Atwood with cases of beer to get my structures done. But then it got really, really easy, and we got wonderful infrastructures that can support the spectroscopy, the crystallography, and so forth. So synthesis and characterization has become extremely easy, and a lot of work is just in that. But I think we go through another phase where reactions and reactions mechanisms will become what we have to do, what we have to understand, and that will probably involve a new wave of fast kinetics, instruments that we can more carefully monitor what's going on in that reaction profile. And I don't know what instruments, what spectroscopies and what techniques are going to be around the corner, but I suspect there should be some new ones.
I think there are threads from both of what you said. Don, if I have it right, and I tend to agree with you there, the best collaborations are one-on-one and bottom-up as opposed to necessarily top-down. Would that be?
Yeah, I think sometimes forced collaborations, you don't really get your money's worth from them. I always find that if I have this strong interest in solving a problem, I'm going to get the most out of it, and people are very willing to interact. We don't have to pay them to interact with each other because we want to solve our problems, and that's the driving force, so we're going to interact.
The other part is, the user interface for all these techniques, for X-ray, for DFT, for NMR, has become so easy that students today are asked to work on projects of greater scope than we did. A couple of crystal structures, we could get a thesis 40 years ago, but now that's not the case.
Right.
So we asked them to really do a greater scope, and this then necessarily takes them into a collaborative mode.
Right, and I do have to say that centers for special spectroscopies are really needed. EPR at an advanced level, for example. I mean, I spent my first 30 years of my career avoiding radicals, and now everything I do has unpaired electrons in it. So I really need EPR, I need Mossbauer, and I have to collaborate outside for those. We have collaborators in Germany. I wish there was more money for travel, for students to travel and stay at places. I think there's some modes of funding that needs to be addressed at the national level that will allow more of that to occur at the student level, other than just my grant funding this. There could be student applications for travel funds.
Okay. I want to turn to a different subject. Inorganic Chemistry, the journal, is celebrating its 50th anniversary year. Both of you began your careers, I guess, shortly after inorganic chemistry started. In fact, Ted Brown was one of the early associate editors of Inorganic Chemistry. So how did you view the journal way back and today, and what do you see going forward? So let me start with how you viewed IC in the early days.
Well, in the early days, I was happy to get a publication in wherever it was, but inorganic chemistry was inorganic chemistry. That's the fundamentals of our field. And I guess we just switched from nuclear and inorganic. Was that it?
That was one of the early things. Before inorganic chemistry, the journal started. There was, I guess, inorganic chemistry was in the division sort of under physical chemistry and inorganic and nuclear chemistry. But that goes way back.
Yeah. Well, I've always viewed it as the journal for fundamental inorganic chemistry, and it's stayed that. It has expanded, of course. Are you asking us now about the broader view of inorganic? But it's expanded. The journal, though, has always had high standards. We do consider JACS to be a little bit higher. No, we can't talk about that. but,
More general.
Yeah.
More general.
Yeah, but I mean, it's an extremely fine journal, and I'm very proud of the publications I have there.
Yeah, I think the journal has become a lot more diverse, but at the same time, I think that's really good, because I like a journal where I can go through that, every issue of that, and run into different things, as opposed to a more specialized journal where the areas are more confined. But we published the first part of my thesis in '67 with Ted, and I think I started receiving inorganic hard copies in '64. So I had all the issues, which I've now gotten rid of because I don't need them anymore. But so inorganic has always been sort of a major place that was a focus point for submitting publications. I was always proud of the papers I published there, and I always kept track of what's published there, and we still do. So it's a major player because you can find things from organometallic to solid state to coordination chemistry to bioinorganic. And it's really nice because you get ideas from all these areas.
I think that's a very, very good point. One of the challenges, I think, in a traditional, I'll call it traditional discipline journal, whether it's inorganic chemistry or Journal of Organic Chemistry, is the fact that today, with people are looking to have their bioinorganic chemistry read by biologists, and people doing materials might be interested in having their papers read by materials and polymer chemists, and energy, the same thing. So how you try to keep the forces that pull people looking for different audiences in with regard to this central foundational concept journal. And I think it really does provide crosstalk between people interested in different areas where inorganic chemistry has a footprint.
Well, don't you think keywords in the abstract can alert people, alert different areas or different disciplines?
I think they can.
What's in this paper?
Mm-hmm. I think that that's a possibility. I foresee when people might sit down and start searching, and they will go in. They're creating, in essence, a virtual journal of their own, whether it's in polymers or polycarbonates or whatever, and they can pull that up. And they may enter these papers without ever going through a specific journal.
Yes, that's
So,
a little
yeah.
scary, but I think it's what has to happen. It's a little scary in that you can miss manuscripts, you can miss information in papers that the author of that paper doesn't even understand what's important, what's of universal importance to other areas.
Do you have a view of what our challenges are going forward for inorganic chemistry and how we can take advantage of those challenges?
With regard to the journal.
With regard to the journal, there's a question about all journals,
Yeah.
Mm-hmm.
okay, and we'll get to that.
Papers,
But with
yeah.
regard to inorganic right now,
I think well, inorganic, I'm not sure there's a specific challenge, but certainly there's a challenge to all journals for the review process. Getting competent, timely reviews is very difficult because once you establish yourself in an area, you just get bombarded from all over the world now with the internet, all asking you for a 2-week review time period that I get the feeling sometimes I could just spend my whole career just sitting in my office reviewing proposals and papers and not teach and not do research or anything else because
Stay busy.
it's that much in. So I think that's always going to be this issue of keeping papers at a high level because you need the expert reviewers, etc. I think we want to be careful not to let too many, the journals are, if you look at it, for example, ACS has come out with Catalysis, Royal Society has a Catalysis now. Well, papers that would have gone to inorganic now going to start filtering into those. And maybe there's a point where we need to slow down the growth of journals.
that's something we have talked about.
And it seems like almost a worldwide competition.
There certainly is, right, there certainly is a competition on journals.
And so you can dilute the area by having to, we can only follow so much literature.
Let me pick up on the reviewing process. As an editor, and you folks as participants in this, I believe very firmly in peer review. I don't like the idea of unpeer-reviewed journals and that the science gets out there that does get published is stronger. What's your opinion?
Well, and that's the way I think Inorganic Chemistry, the journal, will stay strong, is if the peer reviews are strong and are rigorous, and the acceptance rate or the acceptance of only good papers, the publication of only high-quality papers, that makes the desirability to publish in that journal is greater. So it's the way you have to keep the quality up, I think.
Any thoughts on how to serve the global inorganic chemistry community? It's incredible. We are a truly global community today. We probably get more papers from Asia than we do from Europe, and go to any of these meetings and you have people from all over the world. And our community, the inorganic chemistry community, is truly global. Any thoughts on how to better serve that community through our medium of communication?
I guess I don't know exactly what could be done differently because of the internet and English, thank goodness, is the language of choice for science. If there's any possibility of helping with the sometimes with the manuscript preparation in English is a little bit difficult for our international
There are
publications.
efforts to prepare videos and to help people where English is not the primary language.
Right.
And this is particularly true for China, which is now the second largest contributor of papers' contributions to inorganic chemistry, and how to put a paper together, and the criteria that they should apply to their work in terms of where to publish it. I think we do that. Let me turn to, we are going paperless, and I know this is harder for more senior folks, and at the same time, our students do not look at hard copy journals. Our students access all this information electronically, and what's your thoughts? Have you tried the mobile application? And
yeah, we both have the application on our iPhone, and there's some real advantages to that. You can articles of relevance to your students, you can zip them emails right away to read, be sure and read this articles, and you can do this wherever you are.
Starbucks.
So, yes, so that's very useful. At the same time, what I found in my career when I was reading the hard copies was that often just turning the pages, I saw things that interest me that I don't see now because I don't turn the pages. I go to the internet and I look at the abstract, I look at the synopsis figures, or those are very, very handy. But it's not quite the same as turning the pages. And I think we've gotten to the point now where very few of us turn the pages of any journal. And so there was something that I think I'll miss by doing that. But nevertheless, there's so much information now that it's impossible to ever consider going back to those days.
You touch on a point, is browsing,
Yeah,
and being able to see something, the accidental
Yeah.
observation of something really interesting.
Don't you think we ought to be able to replicate that somehow with our
Absolutely.
Nooks and our Kindles and just our readers?
Well, I think you're absolutely right, and we should be able to replicate it, but we're not going to actually do exactly the same thing. There will be different kinds of browsing, perhaps. As you look at the table of contents, if you want to scan through all the figures of a paper, you can do that. And so that might turn out to be how our students browse,
Right.
rather than how we browsed.
Right.
So
Yeah, I think we couldn't expect to browse as we did in those days now, because there's just a lot more publications that we need to be browsing.
What's going to happen to your covers, you know, which had been for a while? This was something that everybody aspired to have a cover on they could frame.
Actually, what we have done is, if you will look, there's a slideshow each issue of 4 different TOC contributions. And we are featuring that on the covers of our different issues, and more like an album, if you will. But I think the idea of having individual issues also comes up to question, because now papers can go ASAP. There are all kinds of interesting questions that come up here. I don't know the answers. And all I know is it was totally different 15 years ago from what it is today, and I don't have a clue what's going to happen in 15 years.
So
Yeah.
you did such an incredible job of moving the journal from the old days to the new days that we're expecting a lot out of you.
That's a tall order. So, thank you very much. With this, we'll conclude our interview, and I want to thank both Marcetta and Don for being here and agreeing to this conversation about inorganic chemistry, little I, little c, and all its related fields, and inorganic chemistry, big I, big C, and how journals are progressing. I hope all of you viewers have had an interesting time watching this. Thank you for sharing.